Welcome to KIN 425 for March 31st. For today's lecture, I'm going to go over some important points from the journal article summaries that were posted by Ashton and Maeja. So both of these summaries have to deal with training at altitude. So this first article, you can see the title of it is Impact of Energy Availability, Health, and Sex on Hemoglobin Mass Responses Following Live High, Train High Altitude Training in Elite Female and Male Distance Runners or Distance Athletes. So this uses a model of Live High, Train High Altitude Training in an attempt to improve hemoglobin mass and performance. This is as opposed to the model that I mentioned in the altitude lectures of Live High, Train Low. So Live High, Train High is just a different model and a different attempt to improve performance in elite athletes. So as the name implies, it involves living high and also training high, so at altitude or with low inspired amounts of oxygen. One thing I want to point out here is Trent Stellingworth is one of the authors on this paper. He is located in Victoria at the Canadian Pacific Sport Institute. If you're ever out there and you're doing any type of research, he'd be a good guy to work with. Good Canadian guy. And he's on this list of international authors for this paper. So this paper dealt with a lot of elite middle distance runners, long distance runners, and race walkers. A lot of them were Olympic athletes. So this is quite a good group to look at. And they were involved in this Live High, Train High altitude camp for 3 to 4 weeks. And the most important findings from this study, so they compared males versus females. They looked at duration of altitude exposure. So some of these athletes had more altitude exposure than others. And they measured hemoglobin mass and improvements in aerobic fitness. So they found that actually, I think they just measured changes in hemoglobin mass in this particular study. I'm not sure if they actually measured aerobic fitness. Anyhow, they found that females responded better than males. So this is kind of a cool study because it also deals with sex differences. So females responded better than males for increasing hemoglobin mass during this altitude exposure. This might be due to the fact that females have a lower hemoglobin mass than males at baseline. So maybe they have a greater room for improvement. Other important findings of the study is that they found that those that experienced altitude sickness had less of an increase in hemoglobin mass versus those that could stay healthy. And they also found that there was a dose-response relationship between altitude exposure and increases in hemoglobin mass, specifically in the males, but not necessarily in the females. I'm going to scroll down here a bit and show you the most important graph from this study that kind of highlights the results. So this nicely highlights the results of the study. So it shows the percent change in hemoglobin mass on the y-axis with this Live High, Train High altitude camp. And they've graphed the low, moderate, and high doses of altitude exposure. So some athletes had a greater number of hours spent at altitude than others. Two things you notice from this graph is for the males, you can see that there's a dose-response relationship for changes in hemoglobin mass and altitude exposure, whereas there's less of a relationship in the females. Another thing you notice from the graph is that overall, you can see the females responded better than the males for change in hemoglobin mass with this live high, train high altitude exposure. So this was for 3 to 4 weeks, and these bars represent the percent change in hemoglobin mass over those 3 to 4 weeks. So a dose response relationship for altitude exposure for the males. So they varied in the number of hours they spent at altitude. The greater number of hours they spent at altitude, the greater the increase in hemoglobin mass. You can see the trend is there for females, but it's not significant. But overall, you can see the females had a greater response than males, which is kind of an interesting finding here. So those are the main findings from this first study. The second study that Ashton and Meja presented is titled here we go. It's comparison of live high, train low in normal baric versus hypobaric hypoxia. So recall that in my discussion of these two conditions, that one is done usually at sea level, so normal baric hypoxia, and hypobaric hypoxia is usually done at altitude. So that's what they're comparing here, is two groups of athletes that trained under these different hypoxic conditions. And this study involved mainly, I believe it was triathletes. Let's see here. It was endurance athletes, and they were all well-trained triathletes, you can see. So one group was exposed to, and this was 18 days of hypoxia under either normal baric hypoxia or hypobaric hypoxia. So just a refresher here that your hypoxia is determined by your PO2 in your expired air, so the pressure of oxygen in the inspired air. If it's low, then it's a challenge to get oxygen into the lungs. So in hypoxia, the PO2 is lower in the air, and for normal baric hypoxia, it's normal atmospheric pressure. So the normal atmospheric pressure is usually around 760 millimeters of mercury. So your atmospheric pressure in this condition is normal, and your hypoxia is determined by a lower fraction of inspired oxygen. So in this case, it was about 16% as opposed to 21% in the manuscript. Hypobaric hypoxia, on the other hand, is what you would experience normally at hypoxia, and that is caused by a decreased atmospheric pressure and a normal fraction of inspired oxygen. So in this case, the fraction of inspired oxygen would be 21%, and the hypoxia or decrease in PO2 is caused by a decrease in atmospheric pressure. With normal baric hypoxia, the hypoxia is caused by a decrease in your fraction of inspired oxygen. So I did mention that there are some studies that show that the responses to these two conditions is different. And Uh, Essentially, that's what they found in this study, is that some of the responses were a little bit different. So um, the study found that breathing frequency was more affected by the hypobaric hypoxia. So there was a higher breathing frequency, which tells you that the stress felt in this condition was greater in the athletes than in the normal baric hypoxic condition. Another thing that they found in this study was that the saturation of oxygen in arterial blood, so this is represented as SpO2. It's the saturation of oxygen on hemoglobin in the arterial blood. Um, this is essentially a measure of the percentage of oxygen that's bound with hemoglobin. Usually it's close to 100%. In hypoxia, it's going down to close to 90%. It was lower in the hypobaric hypoxic condition compared to the hypobaric, compared to the normal baric hypoxic condition. So the hypobaric hypoxic condition appeared to be more stressful. It elicited a greater breathing frequency or greater ventilation compared to the normal baric hypoxia condition, and it also elicited a lower oxygen saturation in arterial blood. So that's on the hemoglobin than the normal baric hypoxic condition. So it appeared from this study that the hypobaric hypoxic condition was actually more stressful than the normal baric hypoxic condition. Other important findings from the study were that both conditions, by the end of the 18 days of altitude exposure, both conditions elicited a similar increase in hemoglobin mass and VO2 max. However, the hypobaric hypoxic condition elicited a greater improvement in running performance, specifically at 21 days after the hypoxic training camp. So I'm just scrolling down in this paper to show you the graph that represents that. So this graph represents the relative change in 3-kilometer running performance in these athletes. And a decrease in this line represents an improvement in performance because it's a decrease in the time required to complete the 3 kilometers running. So the two conditions represented here are your normal baric hypoxia and your hypobaric hypoxia. So the hypobaric hypoxia is down here. The normal baric hypoxia is over here. And you can see that this is the pre versus post 18 days of hypoxia. And then they assess performance 7 days after hypoxic exposure and 21 days after hypoxic exposure. So these two measurements are done at sea level. And you can see that there was a significant improvement in the group that was exposed to hypobaric hypoxia by 21 days post-hypoxic exposure compared to the group that was exposed to normal baric hypoxia. So overall, I think the hypobaric hypoxia elicited a greater improvement in performance compared to the normal baric hypoxia. So despite having similar levels of hypoxia, it appears that the hypobaric hypoxia induces a greater stress during hypoxia, and that's implied by the greater breathing frequency and lower saturation of oxygen in the arterial blood. And it appeared to induce a greater improvement in performance at least 21 days after the hypoxic exposure. So those are the most important findings from these two studies. Again, some interesting studies. Please read the summaries. Yeah, some high quality studies presented by this group for training at altitude.